Okay, looks like we are on air, so that's good. Now, see how far this goes. So, we're gonna go first then. So, out by going over velocity and velocity. So let's say we just have this nice wheel that's going to be rotating. So we talked about there is an angular acceleration, right? We call that omega. So something could be rotating at some sort of speed omega. This is saying that the body, right, the body, it is going to be spinning at some rate for that rate. And we talked about the relationship between, and we said that equals linear velocity equals r. Now, what is that? Anybody actually know what this is saying? Yeah, so that's going to be at some point on this field, there is a linear velocity, right? So let's just say, looking at the point at the edge, right? So if we're looking at this point at the edge, we now know that this point has a linear velocity with this angular velocity, right? But this angular velocity is the same, okay? But this linear velocity is going to change based on radius. Okay? Vectors. Say that this one is much greater than this one, much greater than that one, right? So, you know, if we go 1, 2, 3, we can say V3 is greater than V2. That kind of makes sense. We'll say that we're kind of like taking a reference from down here. At this point, velocity has to equal 0 if it's making contact with the ground, right? Rolling motion. So if this thing were moving and rolling, we know that there's friction here, right? And that is going to have to be static friction. Right? So if there's static friction, there's enough static friction, this object must slip and it'll just move. So we have our omega, which is just our rotational velocity, and then we have our right? And we come here and we say this could be rotating with some alpha acceleration. It's accelerating now. So this would be speeding up, getting faster, rotating faster, pulling faster. So those are simple terms. So rotation torque is equal to different things. We have our vector form, which is r across the path. So that's saying cross product. This is your torque. This is equivalent to R F sine of theta. So this is saying sine theta. That's going to be force. Some sort. Let's say this is a big torque. And we have a force. Forcing is going to be applied right at the edge, and it's pushing on it downwards. Okay? And this is R is going to be F. Now, if we look at this, you see that this is applied X. And as we find this, torque has to be a force. So this R, there's a vector, right? We can actually kind of extend this all the way past. So we can always translate. So it's technically not over here because R is from, but that's not kind of get our angles. So the angle, something that is always going to be angle. So everyone, not that. So you find this angle, you take sine of theta, which if you look, that would give you downward force. You draw up here. That's your downward force. Actually, so that would be your sine. Okay? Cause this to if I were to put it here, causes it to rotate at some sort of point to accelerate, it's going to pass. So we can also say that torque now is equal to I times alpha. So we use this whenever we talk about a rotating three-dimensional body, and that could be a solid. So this is like linear. Okay? In some kind of ball that ball now has, or if it has like as all the way around. That consider that. Okay? So messy. Be careful. Remember that if you have a three-dimensional body, some sort of solid or hollow body, start thinking torque because you're going to need that to try. Okay? So on the test, if you are, I wouldn't be surprised if you had a problem where you had maybe had, I think this is a problem in the book. You had like a center, it's got a rope all the way around it, it comes down. Bucket. Bucket has some mass. And you're told that this thing is going to accelerate downwards. Right? And this is making a solid cylinder. So the solid cylinder has an inertia. You have to know that. So as this moves, you remember a couple of things. So if you had a this one, then you have mass to gravity mg. right? Forces on this body. No, no energy. Actually, kind of draw this out. So forces. Cool. That would be the mg. Now, actually figure out the same. So look here at a cylinder. So let's look at it from the side. Marker, right, we're looking at it this way. So looking at this side, then maybe down, and then we look at this object. It has a radius. All right, it has this radius r going to this point here. So we have torque. T. Theta, well, theta is right? So that's the torque. Each of the torque value and the acceleration equal to some of the torque that would give us R, T, I, and the equation of T. What's the relationship between alpha and acceleration? Over R. Right? So would be all these equations. Down. Let's see. Let's see. So, so kind of all over this. Any questions so far? So, the things I want to go over. So, so that was mostly talking about inertia. I know I didn't really kind of go through and explain it. Inertia is defined as the sum of m I squared. Okay, so that is all of the mass in the system times the radius from the point in the system gives you your inertia. That radius squared. Sorry. So all the mass in the system times the radius squared in the system. From all those, you get the inertia. Right? So what this is kind of saying, well, this is mass kilogram times radius, which is usually measured in meters squared. So this inertia term is your inertia for a three-dimensional body. So you're looking at the mass times the area, right? Mass times the area. So what this is, it's just inertia is the mass spread over an area. It's not divided by, so it's not actually true spread of mass over an area, but it is accounting for the area. So for any kind of sphere, you have to use inertia as the mass, right? So that's kind of all inertia is. You also have another equation. We have the I inertia, center mass plus, and this is the parallel axis theorem. It's saying that the inertia, the new inertia I equals the inertia at the center mass plus the mass times squared with the is the distance this new eye is away from the center of mass. Okay, not our distance from like your point. It's the distance of the new point you're looking at. Okay, from the center mass. Okay, so that's the parallel axis theorem. You probably won't have to do much with these two equations because you will be given a table on your exam that will. This isn't very good. You'll be given a table on your exam that has all of the different things. So if we look book 10.2 will be given to you. Right, so table 10.2 will be given to you. Right, good. Cool. So let me see what else. Go over. I want to go over the rolling problem. I know that I've done it a few times in sessions, but I think it covers a lot of concepts. So let's see. And I'm going to roll down this. So right here. Oh. Friction was slide, not slide. Back slide. So come back over here. What's the mass is equal to lowercase. We say lowercase c. All right. Mass equals c. Going of the object. That's going to be right. So so we have this control. Controlling. Now this one here. So how do we start? What do we so what is causing torque here? Distance from to support, but friction is at support. It's going to be scale. We have R times. That's the we have. I don't say that, but acceleration. Don't really know alpha. Let's go to two. Like so second loss. So what is force? So this point is now, right? Well, we know that the angle are given the exact same angle, right? So this theta, right? This theta is the same as here. So that's an x component plus it's going to act plus that is gravity. That to this equation to say R is F is equal to solve. So, so just F we have negative I A plus A. Cool. So let's get this over this side. M A plus I over R. Okay. The A. Now, I'll just here. We can factor out the A. We have FG sine of theta equals A M plus I. Let's divide this over. We get the acceleration then what we could do, if we wanted to, is you could plug in for I, and you would cancel out a bunch of stuff. So, make sure that I did. So this would be your equation, right? Now, you get a few things in this equation. So we just solved this for any kind of object that's going to roll down a hill. So if you remember Dr. Liu's lecture on the rolled down the hill, he physically rolled a few different things down the hill. He had like a solid ball, hollow sphere, and I think like a hollow cylinder and maybe a solid cylinder. Right? He rolled all those down, and you saw that they all went down at speeds. This equation is what tells you pointing it down there first. I recommend it's a question on your test about it. I would think. I mean, he loves this. I love this. So let's look at that table. So let's just look at the 1 plus I over is 2/5 r squared, right? Right? So this would be 7/5 times the mass. This is for a solid sphere. Now let's look at a third r squared, right? Right? So you get 5/3 now. Okay? For hollow. So 5 or 7. Whichever one is greater is going to cause this denominator, obviously. So the larger the denominator, the smaller the acceleration. So the greater the inertia, so I get a smaller acceleration. All right? So that's that relationship here. So the greater the inertia, the smaller the acceleration. So, like the squared coefficient on that is 1. So you have 1 plus that. So if you don't have a fraction, it's pretty big. It's going to go pretty slow. Right? That should make sense. If you have something heavy, you can hold that lighter object. That really teaches all the concepts of torque, and teaches concepts of just forces again, looking at that, angular acceleration, and I mean, you can talk about the kind of relationship between the angular velocity. At on the body, you get velocities that are different, or sorry, velocities are the same, rotating, but the linear velocity is to go. So that should all kind of make sense. Problem is just using energy, right? So we talked about the fact that there is now going to be rotational energy, right? We no longer just consider the kinetic energy to be 1/2 squared. We now have to consider the rotational energy as well. So if you have rotation, okay, rotational equals 1/2 I instead of k here, say translation 1/2 m e, right? You guys want to do a problem with this? So who wants to do a problem with this? All right, so I have let's say it's okay if I erase this. We good? Let's say we have stop point, right? Other so let's say, right? So whatever it is, rise to the point where this height is maybe 10 meters. Right? The ball is going to come and stop. So the ball is going to start the velocity. It's a marble. It's got a radius. That radius is 1 meter. A really big marble. It's got a mass. Mass of the marble is equal to 10 grams. Heavy. Does that make sense? So, at this, 10. All we have to do is energy analysis. We have 2 points, right? Well, this point A, this point B. 2 points. No forces. Right? So, solve this. So, are equal to a constant. The constant is going to be again. So the final the potential final. Let's look at this. We have an initial. Yes, we do. We have velocity. Right? We have an initial some height. We have a that means velocity is 10 meters. So all that go through and so we have 1/2 squared for now potential. So that's 1/2 squared. To solve the object has a root thrust, that means it has to have object plus equals over here. M. So we have an initial velocity. Right? We could use 0.1 meters. Here's the velocity. 1 times 5 or squared over r squared have our nodes. Right? That's all there is. So, any questions? I'm going to come back to so initial. So kinetic energy of rotating ball. So it's 3-dimensional, right? It's inertia. It's always going to have one of them. It's going to be a combination. It's rotational. It's always going to equal like. Just remember So always going to be, or if it's spring, we'll have KX. Okay. So does that answer your question? Any other questions about chapter 10? Everybody doing all right? Making progress? Cool. So chapter 11. Over that. Chapter 11. Campus space. A few concepts that we really need to go over. So this is rotational vectors and angular momentum, right? And for that, I'm going to be posting. Some of my notes on Blackboard. And hopefully, review. And if you haven't seen, on Blackboard, I posted 2 other documents. One is a static equilibrium document. The other one is simple harmonic motion. They cover chapters 12 and 13 pretty extensively. So if you get a chance before the test, I recommend you try and take a look at those. They should be a little helpful. The static equilibrium one walks you through a static equilibrium problem, like step by step, and they're always the same. So you can look at that. Hopefully that's helpful. But back to chapter 11. So chapter 11. So chapter 11, all it is you're just kind of looking at your angular velocity, angular acceleration, and the way that those kind of work. Or visualize a little bit more. They first talk about the right-hand rule. So for any like angular velocity or angular acceleration, the right-hand rule. Let's say we have a rotating angle, right? What would be the direction of the actual angular velocity here? Into the board, right? So you wrap your hand around with the direction of the rotation, and your thumb points in the direction that this is actually the angular velocity. Okay? And now we have acceleration, right? So we have angular acceleration going counterclockwise. What's the direction of angular acceleration? Outward, right? Cool. So that would mean that this is slowing down, right? Because if angular acceleration opposes the direction of angular velocity, it's going to be slowing down. The same thing as saying for linear velocity, you have negative acceleration, right? This object would be slowing down. If you're moving in that direction now, it has an acceleration in that direction. Okay? So you can kind of look at the system and understand how angular momentum. So we find momentum as mass r cross r cross p, but that is so p is the linear momentum, right? And we said p is equal to m times v. So knowing that we have m times v, right? We can plug this in. We can find that the scalar equivalent of this equation is r. Okay, so that is your linear momentum. Or sorry, your linear momentum is equal to r. This is your linear momentum. Right. Okay, so plug that in, and you can find the angular momentum. Now, this equation and use it in angular terms. So those times omega. All right. So F equals I omega. Think about this. Alpha is equal to I times omega. And right? Torque is angular acceleration. And if we think of F equals ma, that's linear acceleration, and then v, linear velocity, right? So these are related in a way, like that should be kind of there, how that works. So you have these. If you were given a problem, it would be pretty apparent. So one that you could see is conservation of linear or angular momentum, right? So conservation of angular momentum. And that implies that our change in momentum is zero. There is no change in momentum. What it just means that L is observed. So we can say L initial is equal to L final, right? So we have a problem. Let's say you have around any set of masses that exist. So saying that this thing is moving initially, all of a sudden it's a mass. Well, it's going to be that. Initial, final, and work. So we have those two. I initial, I omega final, initial equal I final, omega final. Then you know that if you change the final inertia in some way, there's going to be a change in the final omega, right? So let's just kind of look at this. So we have initial inertia, and we know angular velocity. Let's say we increase the mass, right? We know that I is equal to mr squared typically, right? If we increase the mass by adding this new point, then we would end up decreasing the final angular velocity. Does that make sense? Right? So if this increases, that gives you a larger denominator, which creates a smaller final number. Okay? So the more mass you put on something, the slower it's going to move. Right? So that, I would recommend you go look and read 196, 197. General understanding for precession and the gyroscope, but I wouldn't spend much time on it. But other than that, that's pretty much all there is to chapter 11. So there's really not much to it. There's only a few pages. If you have the time, I would recommend you guys all read the book if you haven't. It's very helpful to read the book because it explains all of the variables. It explains all of the equations pretty in depth. You'll gain a better understanding for what Dr. Lou is talking about in lecture. Okay? So if you have the book, please read the book. Also, the example problems, they are fantastic, they're helpful, and they are typically a lot like what shows up on the test. Because Dr. Lou, whenever he's in lecture, if you ever paid attention to the problems he does on the board, they're the example problems. So, and he has talked about how, like, if you come to lecture and you pay attention to those example problems, will benefit from the test, right? He's told you guys that before. So, if you pay attention and you look at those example problems, you can, right? So definitely understand all the example problems as much as you can. Understand all of the homework problems, which you did post today. So if you haven't looked at that yet, you can look at that. But, sorry, that was kind of a tangent from where we were at. Anybody have any questions about chapter 11? What's that? By the way, I think we signed that sign-in sheet somewhere. Yeah. Oh, that's chapter 11. sure nobody has any questions yet about anything. Check. We'll just go to sleep. So, one check. Direction of, you can find direction. So, torque. Let's say torque is in this direction, right? All right, we're gonna, there's a force in this direction. You know, our radius is here, right? So, what direction do you think it would be? Out. Because you can think of radius, you know, we'll draw in a tiny little vector just to kind of show the vector direction of the radius r across f out of the board. Yeah, pretty much. That's how you would decide, right? So you would just use the unit vectors to kind of see it, because unit vectors only have direction. They don't have anything about them. So if you had a force going off in this direction, radius of this way, right? Radius, then you would know that here's that force. Well, force is off in this direction. So draw the line r across f, right? All right. Any other questions? Cool. So chapter 12. So I'll let you guys kind of find out less good than actually doing. So about the box is about 6 meters. Force 2. Force 2. Force 1. To the left, right? At 10 meters. Then we have force 3 pulling with 3 newtons. Force 3 newtons. Okay? We have one more force acting right here at the center mass. That is force 4. We're going to say that that's 2 newtons. All right? I want you to find the force 2 required to tip this. Right? So we want this way. Right? What would be the maximum force? So we also need to know this standard. Say this. Okay. All right. So how would you guys? I want you to at least walk me through this. All right, how do we start? I'm going to see. Okay. Sure. I tell you. Point from force 2 to the top is. All right. What is so much torque sensitive? 0. So in order for this to just start to some of the torque sensitive 0. Now, what point do you want to find? Some at what point do you think you need that? Bottom right? Right here? Do that. Right? Anybody else want to pick a pinpoint? We can do a few different ones. Center bottom or center right? Doesn't matter. Okay. You can do it right here. Okay. Point right here. Or you can do it right here. All right. Now let's kind of talk about why. Not here. Okay. So that would give you the friction force. And what forces do you have on here? Gravity, which acts right here, right? Other force did I draw in? One more. Normal force right here. It's technically on the ground, right? So we have a normal force and a gravitational force. If we pick the bottom right, what does that mean? How many forces are we dealing with if we pick the bottom right? See if they count for all these. 1, 2, 3, 4, 5, 6. But the frictional force is gone. And what happens when we pick the bottom left? How many forces? 6. Frictional force is still gone because there is no perpendicular distance between the frictional force and this point here. These two points have a perpendicular distance between this point here. We have. How about the center? How many forces do we have to deal with? Frictional force has no distance from the center. Normal force has no distance from the center. And the mass has no distance from the center, right? Because torque, R, F, sine theta, well, right here, no R distance between this force running along, and then no R distance this way here. Okay? So if we know that, we can go through analysis. Let's kind of start. Let's look at force 4. Right? So we know that we have some R. What would the R be for? I mean, 10 meters times force 4, which is 2 meters, right? Now, RF is 90 degrees. 1. R is 10. So you see, like, here to here. Okay. Think about this object as just one force going to be pulling all along here, right? So, force point here. What is the perpendicular distance? So this force is applied. So it doesn't really matter how I draw this in. I could have drawn this pushing over here. I could draw it from the middle. Right? It's still going to be a force that is acting along this part of the object. Does that make sense? Cool. Yes. So we would have 10 meters, 2 force 4. And this sine of theta is 90 degrees. That means it's 1. It's got R times F. Now, is this going to be a positive torque or a negative torque? It will be negative. Why? We assign notations in class that are kind of arbitrary decisions. We all get the same types of answers. So we always assume a clockwise rotation is negative. Always assume a counterclockwise rotation is positive torque. All right. So in this case, this force is trying to pull along this way. So that would cause a clockwise rotation. That was the only force. So that means this is negative. Now, we finished force 4. Let's move on to force 2. Right? So we know force 2 has a distance of 16 meters. All right? So we have 16. We write it force 2. Now, is it positive or negative? Right? Because again, force 2 is trying to push block. So we're going to say something. Right? And that's how we have it drawn. Now, what would happen if force 2 comes out to that far ahead? You know, let's say we solve everything, we find it comes out to be negative. What does that mean about the way I have force 2 drawn? It's actually in the opposite direction. That would mean that I'd be pulling, which isn't going to happen for this problem. But that's just, you always need to draw in the signs and have it drawn in your figure, which is why the drawing is so important. Okay? That's a small thing you won't have to deal with. So, all right. So that's force 2. Now let's look at force 1 and force 3. All right, let's start with force 1. How far away is force 1 from the pivot? Yep, 19. So positive or negative? The direction I have force 1 drawn. Positive, counterclockwise. So 19 times force 1, which is 10 newtons. Now force 3, right? Positive distance. What's that equal to? 0. Right? So we have negative 10 times 2 minus 16 times 10 equals 0. So force 2 and force 2 would be the force. Problem is to find some of the torques. Now, if there were 2 of them, you could actually solve for 4 points in this object. Force. Right? I could have told you that there was a second force. Static. So we can also do that, and then we have to use some of the forces. For static problems, there is no torque, no rotation, there is no linear movements. Some of the forces can't be so. All right, that is this problem. That is all you need to do. I don't have an answer, but you was not too hard for the operator. Okay? Another problem that's hard. If you want, because it is already 5, so we only have 5 minutes left. So if you ask right away. Okay? kind of showing up now. That's good. All right, let's move over. All right. So, is holding an object over the side, right? So we know that there is a line holding the crane, right? Also, another line holding up the crane. There are two lines holding up this crane. This theta, 110 degrees, okay? This theta here, theta prime, we're going to say is 30 degrees. Mass, so the crane is holding up 100 kilograms there. And then I tell you, the center of mass of the crane is about right here, which is 1/3 the length of the entire L, where L is the length of the crane, and L is going to equal 40 meters. All right? And the last thing, the mass of the crane itself is equal to 200 kilograms. All right? So to run through this one more time, your crane, it's got two lines that are holding up and say that it's still changing. So you got some cheese holding up this crane, while it's holding 100 kilogram mass at 40 meters along the crane. So it's all the way at the end of the crane, right? So what we find, this is line 2. I need you to find the forces in the line to hold this crane. Okay? So what is it going to take to actually hold this crane? All right. So we have two things that we don't really know in this problem. So how are we going to solve this? So sum of the force in the x, sum of the force in y equals 0, and the torques. Everything has to be stagnant, not moving. All kinds of words you can say. Let's start with some of the torque. That's always the best place to start. If you like start these problems, always do some of the torques first, because usually you find the answers. This problem is not equal to, and I'll show you why. We're going to assume that there are no reactionary forces in this problem, all right? And what reactionary forces are is right here. This crane is actually pushing down this point, and there is a force y and a force in the x direction that's holding it back up. We don't know those, so we're not going to deal with those, all right? So we have this, all right, and we're going to take our pinpoint right here. So let's do some of the torques, okay? Some of the torques. Let's start moving up this crane. Right here, center of mass. You always know that there is the mass of the object always acts at the center of mass. That is use trig to figure out the angle. You know, just like if we did a force analysis of an object going down a slope surface, there is the same angle here, right at the pixel prime. Right? So we know that there is the angle between these two, right? So we can find the y component of the force. Okay, so we have force due to gravity. We can find the y component of that, right? And then we know that torques are always equal to RF theta, right? However, you all are here, all right? It doesn't always have to be sine theta, all right? That is what the book tells you. What Dr. Wu told you. It simplifies things because if you have two vectors here, it's always this angle. But in this scenario, if we want the y component of the force, would it be easier just to use cosine, right? Instead of finding the angle, you have to find actually the sine. So we could use cosine, or if you really wanted to stick with this notation, right, you would have to find a different angle. You need to find the angle which would be the angle between the actual crane and the force acting downwards, right? Then you can use sine of theta, because let me draw this one. Force coming down. Crane. Sine. A triangle, this is 90 degrees, got 90 plus 30, so try to say, drop this down, this angle, just because we problems. So, all that. So we need this angle, so that's the complement. So if we do this, we have our mg, so we have first r, the distance r, 1/3 of L. Well, I told you L is 40, so 3, which is r, the force, which is mg, right? So 200 kilograms times gravity, which I'm just going to write in c times g, right? That's our distance times that, but we need the y component of that, so we're going to use sine theta prime. So we can also just do 90 minus theta prime. Right? This is the same as saying 180 minus 30. Right? And then that would give you. Okay, that's the exact same thing. It will be the same angles, right? You can check that on your calculator. But here is that component here. Let's look at the next part. Right? So we move on to this is intention, right? So there is a force acting at that point, which I didn't actually tell you those lengths because I forgot. So we'll say just 1/2 be fine here. Okay. All right. So we want to try and pull L so that T sine. In order for us to find the sine of this angle, we have it, right? So if we put R going this way, we can draw a little vector saying that R is coming out this way. This angle is that would be the same as saying R as that's what plug in. T1. T2. So let's find. So that is intention. Pulling. So we know that this angle theta prime is the same. So if we decide, so which is 40, sine theta on the end, right? So this is the complement, or sorry, 90 plus 30, we subtract 20, so 180 minus 120. Right? 60 degrees here, right? So we need to find the y component of that, which is pretty easy. So, it's going to be negative. That's a full 40 times the mg. So that's the mass of block, and that's going to be sine 60 degrees. Okay. All right. This is all right. equal to find your angle that you need. And sine of 1,000. Right? In one equation. What do we have to do? Find another equation, right? So I'm going to erase and there's our okay. Yes. All right, now we need force equations, right? T1, T2. We're going to ignore the pivot points, all right? Correct. So let's do some of the force in the x direction. All right. So we have negative T2. Right. That's just. Then we have T1. Right. So T1, we want to find that in the x direction. It could come here. Right. From angle, we know that this angle here is going to be the prime. We know this angle is 110. 110 plus theta prime. Take that. Right. Minus prime plus 110. All right. So that would give me the angle. Cosine. So that would be again in the direction T1 cosine of 180 minus theta prime plus 110. Okay? And then some the forces combined. Check out in my folder. Should be in my folder. You will have a process for solving equations. Okay? Right. So far. Any questions so far? We good? Cool. Cool. So you guys want to go over some harmonic motion? Honestly, it is just the equations. If you can understand the equations, you can do the problems in some harmonic motion. So that sheet that I gave you will explain it pretty well. All right? Go over it though. I'm happy to. Anybody go over it? Yeah, go over it. Sure thing. All right, so we'll go over some harmonic motion. All right. Chapter 12. I mean, this problem covers pretty much all of chapter 12. All right. Now, check 13, harmonic motion. Right? There are a bunch of equations for harmonic motion. Okay, so oh wait, you did it? Oh, okay. Yeah, here, I'll try to. All right. So I said harmonic motion. Cool. Okay. So we got this. All right. There are 3 sections we have to know. I want to have actually over here. All right. So let's see. Chapter 13, oscillatory motion. All you need to know are sections 13, 13.1, 13.2, 13.5, right? Back when I said this, that's all you have to know. So all that really entails is just simple harmonic motion. And for simple harmonic motion, you have a bunch of equations. So we'll go through them step by step. So first one, we have frequency, F, which frequency is equal to 1 over the period, right? And that's hertz, or you could say 1 over seconds, which is just seconds inverse. Those are all the different units for frequency, right? So that's what that's equal to. And let's see, U at the period T is equal to the time it takes per cycle. So let's say it took me 10 seconds to do 10 cycles. Your period is 1 second, all right? 1 second per cycle. That's what the period is kind of, okay? This might show up on your test in some way, like just might be given certain information, you have to use the period. So this is just something that people kind of overlook because it's not a true equation, but it is still something. So again, the frequency or the period is the amount of time it takes to make do 1 cycle. All right, so that's okay. Now we start getting into what simple harmonic motion actually is. And the way I described it in my last session, harmonic motion is spring is the best example, and we assume that nothing going to stop the spring from moving. It is going to constantly move. There are no driving forces, no damping forces, nothing that actually changes the spring. Okay, so we have, let's say it is at a position X. Okay, so this is where the spring rests. Now we're going to pull the spring. Now it's at X equals 0.5 meters, right? We're going to release the spring. What's going to happen is this spring is going to oscillate between 0.5 meters and negative 0.5 meters. And it's constantly inside, outside, in and out, okay? And what that generates, that would be a sine curve. So start, so down to 0.5. We release it. It comes down. Now it's at negative 0.5. Right? Cool. So that's what you get. Now, on your quiz today, you had a problem talking about this. So there are some equations that describe this motion. There's X. And then the negative A. Omega. Omega. And then add finally A. That's equal to A times omega squared. All right. So at the maximum velocity, if we have this sine wave, right? At our maximum velocity, what would the angle be in order for the velocity to be at its greatest? Yeah, 9 degrees, I would say. Right? It's because sine of 2 is 1. 1 would mean if you're multiplying A times W times 1, you have your maximum velocity constant. And because sine is bound. Sine is a bound function that can only reach 1. It can only be as great as 1 or as small as negative 1. It does not go past that. So that means that 1 would be the maximum point, and that is where this is going. So if the velocity is maximum at 90 degrees, what would the acceleration be at 90 degrees? 0, right? So if our acceleration is at minimum, 0, right? The acceleration our velocity is at maximum. And then if the velocity is at maximum, our acceleration is at minimum. Right? Same thing. Or if you say velocity is at minimum, which would be, you know, it's not moving fast at all, we're at 0, our acceleration is greatest. Does that make sense? Understand that? So that was your quiz question. Hopefully that made sense. So those are your equations for simple harmonic motion. Understand x here, x of t, it should be x of t. That's just x as a function of time. That gives you position on this sine curve. V sub t gives you velocity on this sine curve, and then a sub t gives you acceleration on this sine curve. And we're kind of talking about a spring all the time, or something that is considered to be in simple harmonic motion. All right, so always in a constant state of sine wave or cosine wave, anything like that, just to that always is bound between one, right, the sine, right, and then it can be multiplied by something, and it's going to have the same sort of frequency, right, and oscillate, yes. So I can change, but it will be set, so you can't really change it without a force. Okay. So that is that, and now you get into, all right, so in here we have omega. Well, that's we also say omega mass. spring constants. All right, spring constants are always measured newtons per meter. So you have a relationship between and 2 pi f. So you could also just well, square root of k, right? This omega has to equal f run with the mean that the frequency is also equal to k over m over 2 pi. Right? That's easy. Just to help you derive that. So, you know, the angular frequency are the same, so you can have a relationship between the frequency and the spring constant, or the mass, all right? So that's just the manipulation that you can see on the test. That would be a like a typical problem you might see for a multiple choice. So next we have, we talked about energy, which is 13.5. So this is all there is to 13.1 of 13. All right, that's simple harmonic motion. Now, the last part, 13.5, is energy, and that's just talking about the energy of simple harmonic motion. So, can I erase this? Everybody good? Cool. I will erase motion. So remember, what we ended up doing for simple harmonic motion is we came in and we derived equations that counted for that 1/2 kx squared for potential. And we ended up coming up with potential is equal to 1/2 k a, the amplitude. Again, k is spring constant. A is the amplitude squared times cosine of that's cosine squared times omega. All right. So all the terms in here, k is spring constant, a is amplitude, omega is time. All right. So that is your potential energy, and we came up with the term for kinetic energy, 1/2, and that's a squared sine. So sine squared. Again, a is spring constant, a is amplitude, omega is angular frequency. All right, and then if we wanted to find the total energy, total, that has to equal the potential plus the kinetic. Okay, and if you wanted to find maybe the ratio of potential to kinetic, wanted to find the ratio of kinetic to potential, right? Or if you wanted to find, I don't know, if you're told like the total energy and you were asked to find the potential of the ratio of potential. Comes up every now and then. For what? No, it's not on there. Just 13.1, 13.2, 13.5, only simple harmonic motion. Okay. So that makes it a lot easier. And then for chapter 14, you only have to know the Doppler effect. So that makes that pretty easy. Okay. So that's it for chapter 13. Any questions about chapter 13? Any questions, guys? No? All right. I don't have any problems. I recommend your homework problems. Maybe the first four homework problems that you had for simple harmonic motion, because those were the easiest ones, and those will be what you'll see. That and like Doppler effect. Again, that's probably going to be a multiple choice question. It's going to be a multiple choice question. So that would mean that you just understand how to do Doppler effect. So can I erase this? I'm sorry, I'm dealing with the boards. All right, so I'll do chapter 14 really quick. Just go over Doppler effect. So what is the Doppler effect? I'm just like, right? Never forget like running across and making that sound. Doppler effect. I loved it. So All right, let's kind of go through it really quick. I don't really have any notes on it, but pretty easy. So, all right. For a moving source, so let's say you're standing still and something is moving towards you, right? That's going to create waves. You have a frequency prime. That's the new frequency of the object. That's equal to frequency that the object is emitting, right? So if it's an ambulance, it's got a frequency of the siren that's going to be blaring, okay? That's the frequency of that siren. Now, it's going to create a new frequency as it's approaching you because the sound waves are catching up to other sound waves and it is condensing louder. It's amplifying it because you're faster frequency because you have the waves that are closer together. It's crunched at a higher frequency. Or minus u over v. Now, u is equal to the, I think it's the velocity of, okay, so it's saying the source is moving at a speed u through medium. So that would be the speed of the, I would think. And then v is the wave speed. What? Although if it's, I mean, this right here doesn't count for that moving way. You could also think that way, but like, so, you know, if it's approaching you, you know that this frequency is going to have to increase. So that means that negative, right? For this equation specifically. That would make the frequency increase. If this is negative, it's subtracting off. This number on the denominator is smaller, which would increase the whole number for the f prime, right? So if it's approaching, you get a larger frequency, so negative. Now, right? So that is for a moving source. Now, if you have a moving observer, so like you're moving towards an object at some sort of speed, you get f prime equals the original frequency 1 plus or minus e over v. Now for this one, again, it's approaching, you now use a positive. And if it's going away, you use a negative. Because if you use a negative here, it makes it smaller, which makes this smaller, right? So if you're approaching an object, you would use a positive. It makes sense for this one. Now for this one, it's the opposite. You have to think about it. Think about how you increase this f prime based on the equation. Okay? I don't think Dr. Wu tells you which of these is which one. So know the scenario. Again, this is for an observer moving. So like I am moving towards the source of the sound. This one is that it's standing still and the source of the sound is moving at them. Okay? That is the Doppler effect. That's all you need to know for the Doppler effect. So any questions about that? Take the silence as a no. All right, cool. Well, that is pretty much all there is to test. That would be chapters 10, 11, 12, and 13, 14, right? So we went through pretty much everything. So if you guys have any questions, please email me. Try and email me either today, tomorrow. That way on Sunday I have some time to answer. I will try and answer as late as possible today, but there are no guarantees. I have a test to study for on Monday, so I will be doing that. But if you have questions, send me an email, and I will try and get back to you as soon as possible. Okay? All right, cool, guys. Well, if you have other questions you want to ask me personally, please stick around. I'm here for another 20 minutes. Okay? All right. For those that are just watching the video, if you have any questions, again, email me, and I will get back to you. All right.